Alright guys, this is our Princeton Review help video, and this is for week 17. And right now we're working on page 97, numbers 1 through 6. Okay, so we're just being asked to find some limits here. Now all of the limits on page 197, 1 through 6, all of them have this form. They're a polynomial being divided by another polynomial. Okay, so the first thing you're always going to try when you're trying to find the limit is you're always going to start with just some direct substitution. Just try plugging the number in directly and see if you get an answer. If you get an answer, that's the answer. If you don't, then it's not the answer. So the next thing we're going to do, if that doesn't work, is you could do one of two things. You can factor and cancel, or you could do L'Hopital. But L'Hopital will only work if you have 0 over 0 or infinity over infinity. So you got to remember that. So you'll do factoring and canceling, or you'll do L'Hopital. Now, if one of those things don't work, what you're going to do is you're going to take your C value and you're going to add or subtract a very small number from it and plug that in. And your answer, if it's positive, will be positive infinity, and if it's negative infinity, because that means that if well, the first two steps didn't work, it's a non-removable discontinuity. So I'll put non-removable discontinuity, in which case the limit doesn't exist. So what we're going to do is we're going to plug in a number that's really, really close on both the left and the right-hand side of the number that we want. And if you end up with a positive number that's really big, then it's infinity. If you end up with a negative number that's really big, then it's negative infinity. Or if you're doing a double-sided limit and they're not the same, then that would be a does not exist type of situation. Now, I'm not going to do all the problems here on numbers 1 through 6. I'll just do one to demonstrate the steps, but other than that, it's going to be pretty straightforward and to the point here. So let's take a look at number 6. I'll do number 6. On number 6, we have the limit as x approaches 6 from the right. So for this one, I'm only necessarily concerned about the right side. Sometimes that doesn't even matter, but we'll see. X squared minus 4x minus 12. Okay, so we always try direct substitution first, right? So I'm going to plug in my 6. And that's going to give me 8 over this good stuff. And what I end up with then as a result is 8 over 0. Okay, now that's undefined. So direct substitution did not work. All right, so what do we do now? Well, we could try factoring this thing to simplify it. So let's see if we can factor it. And then we're going to go ahead and remove that discontinuity there. And that's going to leave me with this limit instead. Notice I had to do the factoring and canceling approach if I was going to try anything, because this is not a L'Hopital situation. Okay? And don't forget, we don't put equal signs either, right? We put arrows because you can't have equal to an undefined situation. I can put an equal sign here, though, because that is true. All right. Now, as for this, let's go ahead and try to plug in again. Well, if I do my direct substitution, I end up with 1 over 0, which is still undefined. And I can't factor and cancel anymore, and it's still not a L'Hopital problem. So as you guys can see, direct substitution failed. Factoring and canceling didn't work. The last thing we can conclude then is that this is a non-removable discontinuity. Okay, so when you have a non-removable discontinuity, what you're going to do is you're going to take the number that they're asking you to plug in, and you're going to add to it a very small amount. Why am I adding? Because it's from the right. Now, if it was from the left, we would do minus. Okay, and if they don't even have a plus or a minus there, then you have to do both. Okay. All right, and so basically I'm going to be plugging in not 6, but I'm going to plug in 6.001 into my function that they've given me. So that would be 6.001 plus 2 over 6.001 squared minus 4 times 6.001 minus 12. And then I'm just going to use my calculator to figure out what that equals. And I end up with 1,000. And so whenever I end up with 1,000, that would indicate that this limit is going off into infinity. And so my final answer for my problem here is that we had a non-removable discontinuity, and the result is that the limit of the function as x approaches 6 from the right is infinity. And I don't know if it's technically right to put equals there, so I'm just going to say let's not do that and let's just draw an arrow. But we end up with positive infinity, and that's because the closer we seem to be getting to 6, the bigger the outcome seems to be. And what's going to happen is the more close we get to 6 on the right side, the bigger and bigger that number is going to get. And you could test it for fun if you wanted to. Just try plugging in this instead. That's even closer to 6. And what you'll end up with here is an even bigger number. So it gets bigger and bigger as you get closer and closer to 6. So the limit of this function is going off into infinity. All right? And then for numbers 3 and 4, you might want to take a look at the following sheet here that I gave you guys a little bit earlier. Oops, I lost it. Let me bring it back. It's a little worksheet that I put on our Saturday study session thing that I put, but it's also in your 3.9 notes. There's a couple of limits in there where you're finding a limit at infinity for numbers, I believe it's numbers 3 and 4 on this particular assignment. You'll probably want to look at this a little bit. Okay? That being said, then we'll move on to the next set. All right, so this is for page 110 now, numbers 1 through 4. I'm going to do number 1 and 3. So let's take a look at number 1. Is the function continuous at x equals 2? In order for a function to be continuous at x equals 2, first of all, the function's value at 2 needs to exist. The limit of the function as x approaches 2 also needs to exist. And then finally, they need to be the same thing. Now, when it comes to finding the limit of a piecewise function like this, the only way to know if the limit exists is to do the limit from the left and from the right whenever they're asking you to find the limit at a number which is like the boundary point where we're switching from one piece to another. You have to make sure that the limit from the left and the right are the same. If they're not, then the function is not going to work. So first of all, let's figure out what f of 2 is. Now that means what's the y value when x equals 2? Well, there's only one place up here where x equals 2, and it's right here. So the y value for that is 9. So f of 2 equals 9. Now the next thing we need to do is we need to figure out if the limit exists. And like I said, to do that, you need to find the limit from the left and from the right. So I'm going to start by finding the limit from the left of 2, in which case I would use x plus 7. Because if we're coming at 2 from the left, that means we're coming at 2 from values that are less than 2 and that's why we would use x plus 7. And then we also want to find the limit as x approaches 2 from the right, in which case I would use this, because if you're approaching 2 from the right, you're approaching 2 from values of 2 that are greater than 2, right? And now we need to see what those are, and we're just going to do some direct substitution. So if I plug in 2 here, then I'm going to get 9. And if I plug in 2 here, I'm also going to get 9. And so since those two things are equal, that means that the limit exists. And the limit, therefore, is 9. And therefore, we could say that since this equals 9 and this equals 9, those things are in fact equal. And boom, we can say, yes, the function is continuous. So you have a few steps to do. First, you need to find the value of the function. Next, you need to find the limit from the left and the limit from the right. And if those things are equal, you can say that the limit exists. And then finally, you need to make sure that those two things are actually equal. Now, if all those criteria are set, then you're good to make your statement that yes, the function is continuous at x equals 3. I guess to be more specific, we say at x equals 2. All right? And so you'll handle number 2 in a manner similar to that. Let's go ahead and scroll down here to the number 3, though. Number 3 is asking us, is the function secant of x continuous everywhere? Now for that, you're going to want to look at a sheet that I gave you guys a little while ago. This little worksheet I told you guys to put somewhere in the front of your notebooks because you'll need to look at it on occasion, and it's from our lesson 3.3. So if you want to look for it there, you can. But what it does is basically you just find the function you're interested in, and then this column will tell you what the equation looks like. This will tell you what the graph looks like. This will tell you where it's continuous, and this will tell you where it's discontinuous. Okay, so we're looking at secant graphs right now. So I'm going to scroll down to where we see the word secant, and there it is. And secant functions have discontinuities for all those values of x where it makes the argument some multiple of pi added to 2 pi. Now that's kind of complicated, but the point there is essentially that no, secant has discontinuities. So secant is not continuous everywhere. So no, secant has discontinuities when x equals pi over 2 plus pi n, where n is an integer. In other words, if you just add some multiple of pi to pi over 2. So for instance, if you were to start off at pi over 2 and we added pi to that, what would we get? Well, you have to put that over 2 and make it a common denominator, and you get 3 pi over 2. So secant is continuous from pi over 2 up until 3 pi over 2. But at both of those endpoints, it's discontinuous. Okay? Now, if I were to include brackets, that would mean the endpoints are included. Okay, now, but we know that these are points of discontinuity, so we don't want to use brackets there. We want to use parentheses, which would indicate, well, it's continuous in between those two numbers, but not at those two numbers. Okay, and so that's going to help you guys answer number 4 a little bit as well. So let's go ahead and call it a day there, and so the rest I'll leave up to you guys to work out and see how you do. And hope that was helpful, and we'll see you guys next time.